Hello juniors, today we're going to see electronic assignment 14. We're going to introduce a new type of function, which is the logarithmic function. This is the last type of function we're going to see before we finish with the topic of functions from the IB, which is one of the longest ones. If you remember, we have seen different types of function. We began with linear functions, then we've covered quadratic functions, then we've seen rational functions, then exponential functions, and finally we're gonna end up with logarithmic function. Actually, there's one extra type of function, but which is also related to trigonometry, which is the topic we're gonna see later. And that type of function is called a circular or trigonometric function, which is a cosine function, sine function, tangent function, so on. That's actually the last ones that we're gonna be seeing this year. Okay, so logarithmic functions, the objectives for today's class are, are two. First, identify logarithmic functions and their graphs, and second, identify relationships between the exponential and logarithmic functions. Okay, so first of all, we're going to define what a logarithm is. It says, a quantity representing the power to which a fixed number, the base, must be raised to produce a given number. We're gonna cover this concept more in depth in the following electronic assignment, but just for you to have an idea of what we're going to talk about today, there's a definition. Okay, what are some real life applications of logarithms? The Richter scale. Actually, I just realized I'm missing an H here. The Richter scale, which is used to measure the intensity of earthquakes, uses a logarithmic scale. The pH scale also uses logarithmic scale. Human hearing, the decibels, are also measured using logarithmic scales. And COVID-19 cases also, I inserted this image here, which is from the worldometers.com, which shows the day-by-day statistics of the COVID-19 cases. And if you see here, you can see graphs of total cases and total deaths, and you can select either if you want to see this using a linear graph or a linear scale or a logarithmic scale. For both cases, I put a logarithmic scale, and you see what happens here. In the y-axis, instead of having a linear scale, which is, for example, going 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, which is what we're normally used to do, you see that the logarithmic scale doesn't go from 1,000 to 1,000 in this case. It goes from 1,000 to 10,000, then to 100,000, then to 1 million. So it jumps in an exponential way, right? We are multiplying by 1,000 in each case. For example, 10K is 1K times 1,000, then 100,000 is 10K times 1,000, and so on. Okay, so that's the logarithmic scale, and it is used to represent very large quantities, or when something grows very fast, we tend to use the logarithmic scale in order to represent this, in order to be able to visualize all of the information. Or else, if we go to a linear graph only, the graph would be something very large, maybe, and maybe not all of the graph will fit. That's why logarithmic scales are sometimes useful, right? Okay, so let's do this investigation together in order to see what this is about. It says, on your GDC, plot the graphs of f of x equals 10 to the power of x and g of x equals logarithm base 10 of x on the same set of axes. Okay, so that's the first thing we're gonna do. I think I already did the graphing, but I'm gonna do it again. No, so the first function was 10 to the power of x, so 10 to the power of x. That is an exponential function, if you remember. And we're gonna do the logarithmic function, which says log, let me see, log, where do I find log? Log, here we have log base 10 of x. Okay, so log base 10 of x. And there you have both graphs. I'm going to change the scale a little bit. I'm going to put scale from -5 to 5 in x and -5 You can do this in your calculators as well if you want. -5 to 5 in y, okay? So there you see the graph. And the blue one is a logarithmic function. The red one is the exponential function. And there's something that you maybe are able to see already, which, if you remember, these types of graphs, whenever we have it like this, I'm going to do the reflection line y equals x. If two graphs are reflected with respect to the line y equals x, then we're talking about inverse functions, okay? So that's exactly what is happening here. Let's go back to the assignment. It says, so here's the graph, right? I plotted the graph there. Then it says for part B, find the domain range in asymptote for f of x equals 10 to the power of x. If we look at this graph, which is the red one here, the domain are all real numbers, right? So I'm going to write here, domain x belongs to all real numbers, but the range, if we take a look at the range, in this case, it's only positive values, right? From 0 to infinity. It actually does not touch 0, so y greater than 0 would be the range. Now, take a look at this function, at the blue one. What would be the domain and range in this case? The domain, if you take a look, it doesn't go to the negative values, it only stays with the positive x values. So the domain are all values greater than 0. And if you take a look at the range are all real numbers, right? Go from negative infinity up to, this keeps on increasing towards infinity, so it's up to positive infinity. So the range is y belongs to all real numbers. And if you take a look and you compare these two, you see that they are exactly the opposite, right? So that's another sign that tells us that these two functions are inverse functions. Then it says, now plot the line y equals x on the same axis. This is the line. I already plotted this. And you see that they are, both functions are perfect reflections of each other with respect to this line. And that means that both functions are inverses of each other. So what does the line y equals tell you about the functions f and g? Explain your reason. So we're just going to say that f and g are inverse functions. What is the relationship between exponents and logarithms? The same thing. They are inverses of each other. Then it says, how could you use the domain and range of the exponential function to state the domain and range of the logarithmic function? This is what we just saw. It's actually just flipping the order, right? We flip the order. I'm going to write it like that. We flip domain and range. Flip domain and range. Finally, what graph do you get when you reflect the graph f of x equals a to the power of x in the line y equals x? So if we reflect an exponential function with respect to this line, we're going to get the inverse function, which would be, I'm going to write it as g of x equals, and we would write this as log base a of x. You see that here we have 10 to the power of, a to the power of x, and here we had 10 to the power of x, and the inverse was log base 10 of x. Okay, so this number represents the base of the logarithm. So if I have a to the power of x, then that a would represent the base of this logarithm over here in order to be inverse functions. Okay, so that's something important for you to consider. Okay, so that we're done with the investigation. So here's a general conclusion. It says, generally, if f of x, remember this is the same as saying f of x equals a to the power of x. It's the same thing. If f of x is a to the power of x, then the inverse function, this is the same as saying f minus 1 of x equals log base a of x. Okay? If f of x is a to the power of x, then the inverse function is log base a of x. Log y equals log base a of x is the inverse of y equals a to the power of x. Okay, So through this investigation, we proved that this is true, right? Log functions are the inverse of exponential functions. So it says properties of logarithmic functions. The inverse of y equals a to the power of x is y equals log base a of x. So the graph of y equals log base a of x is a reflection of y equals a to the power of x in the line y equals x, which is what we're looking here again. So some properties. It says properties of the graph of logarithmic function y equals log base a of x, where a is a number greater than 0 and a is different from 1. One thing is that x equals 0 is an asymptote, and that's a vertical asymptote, right? X equals 0 is this line over here, and you see that the logarithmic function has that vertical asymptote. It never actually touches the y-axis. Then it says the curve crosses the x-axis at 1, 0, right here. Okay? If you remember, and we're going to do the comparison with the exponential function. The exponential function, instead of having a vertical asymptote, it had a horizontal asymptote at y equals 0, right? And then the logarithmic function has an x-intercept at 1, 0, while the exponential function had a y-intercept at 0, 1, okay? So try to always compare it with the exponential function. Then it says the graph continually increases for a greater than 1 and decreases for 0, for a value between 0 and 1. Then the domain is a set of all positive real numbers. That was different from exponential function, where in the exponential function, the domain was all real numbers. And then it says the range is a set of all real numbers, while in the exponential function, the range are only the positive y values. Okay? So those are the properties that you should consider for logarithmic functions. Then it says, observation. The same rules of transformations apply to logarithmic functions. So all of the rules of transformation we have seen, translations, reflection, compression, stretches, all of that applies in the same way for logarithmic functions. Okay. Finally, there are two types of logarithms that we're going to center on. Actually, there are only two that exist, which one of them is logarithm to the base 10. Whenever you see, for example, this, y equals log of x, when there's no number here, there's no base, implicit base, we assume, no, it's not that we assume, when there's no base, it is, the implicit base is 10, okay? Just as when we write, for example, instead of, for example, 2x, when I write it this way and I don't write an exponent for the x, we assume that the exponent is 1, right? So same thing occurs with log. Whenever you see log of x, there's an implicit base of 10, unless the exercise explicitly states another base, for example, log base 2 of x, okay? But when we don't see a base, we assume it's 10. Then we have natural logarithms, which is the other type of logarithm. For example, it says y equals natural logarithm of x. Whenever we see ln instead of log, we're talking about natural logarithm, which basically is the same function, but it changes the implicit base. Instead of being an implicit base of 10, whenever we see natural logarithm, the implicit base is e, okay? The letter e, which is the one we saw in last class, right? E is a number which is 2.71 and so on, okay? So those are the two types of logarithm, but the properties, the asymptotes, the intercepts, everything is the same for both functions, okay? For the logarithm to base 10 and for the natural logarithm. Okay, so if y equals natural logarithm of x, the inverse of that function would be y equals e to the power of x, okay? That's the exponential function, which is the inverse of this natural logarithmic function, okay? We're going to see all of these properties later on in future live sessions. So I'm going to close this electronic assignment by doing this example. It says, the function f of x equals log base 10 of x minus 2 plus 1 is given. So for part A, it says, describe the transformations necessary to transform the graph g of x equals log base 10 of x onto f. Okay, so there are two things that are causing transformations here. If we compare this function to this function, what do we notice? First of all, the negative 2 inside the parentheses, which if you remember, causes a horizontal translation 2 units to the right, okay? So I'm going to write that first here. Horizontal translation 2 units right. Okay, and then this +1 outside the parentheses is causing a vertical translation 1 unit up. Okay, so vertical translation 1 unit up. So those are the two transformations to map this function into f. Then for part B, it says, write down the equation of the asymptote of f. F is the transformed function, okay? So in order to write the asymptote, we're first going to analyze function g. If function g is the original function, let's say the parent function, the horizontal asymptote, I'm going to write, sorry, the vertical asymptote. So I'm going to write vertical asymptote of gx, which is the original function, should be, if you remember from the properties we just saw, the logarithmic function has a vertical asymptote here, right, at x equals 0. Okay, so the vertical asymptote is x equals 0. Now, if we moved the function 2 units to the right, then the vertical asymptote of f of x should also be translated 2 units to the right. Okay, so the vertical asymptote of f of x, I'm going to change this, of f of x is x equals +2 because we moved 2 units to the right. Okay, so this would be the result for part B. Then it says C. Find the domain and range of f. F is always a transformed function. So if we work with g of x, I'm going to do domain of g of x. If g of x is the original function, right, the parent function, the domain of g, if we look at this type of graph, we saw that the domain are all values greater than 0, right, all positive values of x. So same thing for here, x greater than 0, and the range of g of x, would be, if you see here, all real numbers, right, here. Y belongs to all real numbers. So y belongs to all real numbers. Now, if we work with the transformed function, we're going to say that, let me duplicate this here. So we're going to say that instead of g, this is f. If the function has moved, let me change this. All of this. If the function has moved 2 units to the right, then instead of being x greater than 0, remember our new asymptote is x equals 2, then my domain should be all values greater than 2, okay? And what about the range? Independently of this vertical translation, it is not affecting the range because the range is already all real numbers. So if we move the function 1 unit up, it will still be all real numbers, okay? There's no change in the range in this case, okay? So this is domain and range of f of x. Finally, for part D, it says sketch y equals f of x and the line y equals x on the same graph. Hence, sketch y equals negative f of negative x, the inverse, on the same axis. Okay, so we're going to do a sketch of f of x. If I want to do a sketch of f of x, I need to consider the vertical asymptote and the domain and range. So that's exactly what we're going to do. I'm going to do a sketch here. This is only a sketch, so I'm going to make something quick. It will look something like this maybe. So here we have x, here we have y. One thing to consider, if you remember from the properties, we saw that the x-intercept of the logarithmic function of the parent logarithmic function is 1, 0. Okay, so I'm going to write that here, that the x-intercept of gx, the original function, is the point 1, 0. So what will be the x-intercept of the x-intercept of f of x? If we move the whole function 2 units to the right, then our new x-intercept should be at 3, 0, right? 3, 0, because we moved the function 2 units to the right. Okay, actually, I'm also thinking about the vertical translation, if it affects. Let me see something. If I do if I move, no, we just move this. No, yes, I need to move it 1 unit up as well. Okay, so we're not gonna consider the x-intercept for this. Never mind about this, because that point should be at 3, 1 actually. Okay, so we're gonna do a graph just with the information we have. So I'm gonna plot the vertical asymptote. I'm gonna say that this, for example, is x equals 2. So for that point, I have the vertical asymptote, vertical line, and then I'm gonna plot the function f of x, which would be something like this. Okay, I'm gonna change this to a black. There. So the logarithmic function would look something like this. Maybe, let me see. Something like this. Okay? And then if I do the line y, let me see if I'm down here, sketch the inverse. Okay, so if I do the line y equals x, that line, the thing is I change my scale here. So 2 should be right here. So the line y equals x should be right here. If I extend this, we're gonna get this line. There you go. So that's the reflection line. So the exponential function, the inverse function, should look something like this. Let me see if I can do that. We would have a horizontal asymptote in this case at y equals 2 for the exponential function. So it would look something like this. There you go. Okay, so that's not actually a perfect reflection. I'm going to do this a little bit better. Something like this. Okay, so there you have it. This is f of x, which is log base 10 of x minus 2 plus 1. And this would be the inverse function, okay? This would be f minus 1 of x, which we're going to see how to calculate in later on classes, okay? So that was just an introduction to logarithmic functions for you to understand this. We're going to see this more in depth in future live sessions. So I hope this was clear, and please let me know if you have any doubts. See you.